Okay, so this next podcast in electrochemistry is about the Nernst equation, or another way to think of that is how to calculate cell voltage or cell potential when you're under non-standard conditions. Oh, I just remembered. Why am I wearing the crazy hat and braids? You missed me on Halloween, so this is my cowgirl get-up for Halloween today. So our Nernst equation, the next couple of slides are going to show you how it was derived, but this equation that you see here came from the chapters on thermodynamics and also connecting the Gibbs free energy to the reaction quotient, that kind of KEQ kissing cousin. So on a previous slide in the previous podcast number 5, we learned that you could say that Gibbs free energy is equal to the number of electrons times the Faraday's constant times the cell voltage. Well, this is the cell under non-standard conditions. That's why there aren't any of the little circly guys. And here it is being substituted again when you're under standard conditions. Now you don't need to worry about this derivation because by the time we get done we have a really cool plug in, chug out the answer kind of equation that we can use to find the voltage. So here they are, dividing both sides by the quantity negative n times f. And then apparently if you use base 10 logarithms, I might have done it in a slightly different way, you can simplify it more. And finally, if the temperature is at 298 K, you end up getting an equation that looks like this. And then if I can back up for just a second, Faraday's is a constant, the R value is a constant, and when you combine all of these three constants right here, plus the temperature at 298 K, that's where these numbers here come from. So don't worry about the derivation. It's basically saying E, which is the voltage of the cell under non-standard conditions, is equal to the standard cell voltage, that's this value, which is calculated with 1 molar concentrations if it's a solution, and the temperature would be 25 degrees Celsius and the pressure would be 1 atmosphere. So this is the standard conditions voltage which you would get off of a chart. This is when the concentrations aren't 1 molar. And it's a number that's a combination of constants, 0.0592 over n, and if you remember, n stands for the number of moles of electrons that are flowing in a circuit. And of course, the log of Q, remember, is called the reaction quotient. It's set up exactly the same way as an equilibrium constant. Products concentrations raised to the appropriate power divided by reactants concentrations. So if we can just show you how simple it is to do the plug in the numbers, chug out the answer, sample exercise shows how to get the voltaic cell electromotive force or voltage under non-standard conditions. Now the first thing that needs to be given to you are the concentrations. So notice that these are not all 1 molar. Here is the reaction where we have dichromate ions turning into chromium. So what we're going to do is go, I think, from a +6 or 7, I can't remember, but we have a reduction of the chromium ions down to a 3+. And we have the oxidation when iodide loses electrons to become iodine. So we've identified that we have a redox reaction going on here, and you're being asked to calculate the electromotive force or the voltage of the cell under these non-standard conditions. Well, I know I'm going to have to use that equation of the cell voltage under non-standard conditions equals the standard voltage minus 0.0592 over the number of moles of electrons times the log of the Q. So let's do the Q first. The reaction quotient is chromium ions squared. Don't put iodine in because it's solid, and forget about liquid water. All of those products divided by the reactants, well, that would be the dichromate, no coefficient, so don't do anything to it. The hydrogen ion concentration, wow, it's raised to the 14th. I don't care, it's the number 1, so I can raise it as many times as I want. And finally, the iodide concentration, which again is 1 molar, and we're going to raise that to the 6th power. So you can see that this Q cleans up pretty quickly. It's 1 times 10 to the minus 5 squared divided by 2. and we get a reaction quotient of 5 times 10 to the minus 11. Remember, it's solved the same way as an equilibrium constant. It's just you're taking the concentration under the conditions given, not necessarily at equilibrium. So now we take the standard cell voltage, and maybe you're going, well, where the heck did that come from? You can go back and look at sample exercise 20.6 if you would like. But what we did in that problem was we pulled out the reduction half reaction, dichromate turning into chromium. We pulled out the iodide oxidation, loss of electrons to turn into iodine. We found that we went cathode minus anode, so we went to the reduction potential chart from table 20.1, and we took the reduction potential for the dichromate and subtracted it for the reduction potential for the iodine. And then that value came up to this value, 0.79. So that would have been spontaneous under standard conditions. So we have our standard voltage, we have the constant, 0.0592. Where the heck did that 6 come from? Remember, that stands for the number of moles of electrons. Travel back to go look at section sample exercise 20.6, and you'll find that when dichromate turns into chromium and iodide into iodine, there's going to be a transfer of 6 moles of electrons that were lost and 6 moles that were gained by the iodide. So that's where the number 6 came from. And we have our log of Q, so it's log of 5 times 10 to the minus 11. So maybe it's simpler to do that first. That's where the negative 10.3 comes from. Take 0.0592 divided by 6 and multiply it by negative 10.3, and then take that value and subtract it from 0.79. Well, you can see that subtracting a negative is the same thing as adding a positive. And so what's interesting here is that the voltage is a little bit higher under non-standard conditions than it would have been under standard conditions. And essentially, that is the Nernst equation. Finding the voltage or cell potential, or I should say the voltaic cell electromotive force under non-standard conditions. I'm not sure I can call it cell potential if it's not. And if you take a look at that Q, and we'll practice more on that, there'll be questions about, hey, what would happen if we changed the numerator of the Q value or the denominator? What impact would that have on cell voltage? And we'll walk through those in class using, for example, some free response questions. So that concludes this very mini lesson about how to deal with the Nernst equation. And tomorrow or the next day, I will show you how you can extend that to create a cell with a voltage that is only based upon the fact that we have 2 identical cells and yet their concentrations are different. This will still allow us to have electrons flow through the external circuit. Okay, see you later. Or should I say, adios, partners. Bye-bye.